Hi, we continue the 8.2 Fitting GLM. So now that we introduce the exact procedure, but this does not directly follow from the idea we discussed in the previous video. So actually, rather that we have to use the Fisher scoring algorithm for the likelihood function to get the exact algorithm to get the parameter estimates. So Fisher scoring algorithm is basically the second order approximation of log likelihood function. So log likelihood function, we have basically a function to maximize, or a negative log likelihood that we want to minimize that function. And the method is similar to the Newton-Raphson method. So Newton-Raphson method finds the root of a function using the derivative. So see the figure on the upper right. So this graph. So if we want to estimate the root of this function, and actually the answer is the z asterisk. But suppose we only have the initial guess of the z of 0, then actually if we use the derivative at the z of 0 of this function, and we can get the z1 as a better estimate of a root. And if we continue this procedure several times, then it can approach to the z asterisk. So the Fisher scoring algorithm is a kind of the multivariate version of this for log likelihood function. Yep. So to be concrete, so if we use this algorithm, then the estimating the GLM that becomes this procedure. So at first we have the initial parameter. We need initial parameters, the mu hat and the eta hat, which is the g of mu hat. So here, g is known function. For example, the logistic regression, this is logit function. So this is known function. Then this is iterative procedure. So suppose that the mu hat k and the eta hat k is available. Then we want to estimate the next estimate, the mu hat k plus 1 and mu hat eta hat the k plus 1. So here the 0 and the k are just a superscript, not the power. Okay, so at first we define the zk. So this is so-called the adjusted version of the dependent variable. So basic idea is that we have estimated mu hat, and that is the estimate for the y observation. But we have some discrepancy between this. And this, of course, depends on the observation. And error is sometimes positive and negative. But we want to estimate in terms of eta rather than mu. So if we have the difference between y and mu, that we want to translate this into the difference of eta hat and the corresponding the value z. I mean the z corresponding to y. So how to calculate it? Just using the linear approximation, the zk is equal to zk is equal to the eta hat plus the y minus mu hat times the d eta d mu of mu hat k. So in the textbook it says the eta hat, but usually this is the mu hat k, right? So this is a function of mu. So mu hat k. Okay, so derivative evaluated at mu hat k. Then we calculate the weight of the least square method. So last time in the slide we have seen this variance, but if we make the more accurate argument that we have the d eta d mu. This is probably also I should say the mu hat k, but anyway, so evaluated at eta hat k. So I think the more natural to say this is mu hat k because this is a function of mu. And so the wk, the weight is defined by this, and this depends on the observation. So if we have n observations, then we have the wki. So we have the just the ice term, everything. So and it has the n different the wk. Then that we have weight for the ice observation. Then we can regress y. We can regress y on x with using the we can regress the zk. We can regress the zk on the independent variable x. Then that we can get the estimate, the beta hat k plus 1 by usual the weighted least square method. And once you get the beta hat, then eta hat is obtained. So eta hat is linear combination of beta. So eta is equal to basically beta 1 plus beta 1 x1 plus beta pxp. So we can get the eta hat. Then once you can get eta hat, of course you can get mu hat. So then you can do the next procedure. So this is the procedure, and here so wk that depends on observation. So w should be written as the wk sub I. K is the case iteration. I is ice observation. And if we think about the diagonal matrix with these entries, I mean from I is equal to 1 to n, so this becomes n by n matrix. And using this weight matrix, the weighted least square estimate is here. Yeah, so this y is actually the z in the previous page, but using this formula that we can estimate parameter. So you can see that except for w, you can see the formula that you are familiar with, the x prime x inverse, the x prime y. I mean x transpose the x inverse, x transpose y. So this is usual the estimator for beta in linear model. Yeah, and finally, if you got the estimate, so you get the best estimate for beta naught hat to beta p hat, that is MLE, then we want to estimate the variability of that beta hat. And that is estimated by this quantity, basically x transposed wx inverse. Then if we have the parameter phi, then we multiply the phi hat. And phi hat is estimated afterward. So in the case of the normal case, I mean so in the normal, usual the linear regression, the phi is equal to sigma square. Phi is sigma square. So the sigma square is estimated after we get all parameter estimates. So from sum of squared residuals, you can get the estimate for sigma square. So phi is just estimated at the last step.